is part of the classical theory, is that W is finite. If and only if B, C is at most 3. So there are actually only 4 cases where this happened.
So I missed it, so I'm since I was getting the camera. Can you repeat? So what is the roots? I forget. What are the roots?
I didn't say who are the roots.
No, you said it last time. I forgot. I don't have my notebook here.
For the moment, I
because
just
of Nicoletta.
say that the root lattice is a lattice generated formally by 2 elements, alpha 1 and alpha 2, and that the Weyl group is a group of automorphisms of Q.
You didn't say what the roots are. You said it the last time.
I said it, yes. The roots were the elements which are conjugate to alpha 1 and alpha 2 by the action of W. So all the elements you get.
No, but what is alpha 1 and alpha 2?
Alpha 1 and alpha 2 are the generators of the lattice, the basis. This is a formal lattice.
No, it's formal, but last time didn't you tell us what is the...
I didn't say anything. I said that the roots are the elements which are conjugate to these two elements by this...
yes, but is not alpha 1 the vector corresponding to S1 and alpha 2 the vector corresponding to S2? S1 and S2 are the symmetries.
Of course, if you apply this matrix to alpha 1, this means that alpha 1 goes to minus alpha 1.
Yes.
But this is the definition, yes.
No, so it's not that you didn't say what the roots are. I mean, you didn't say, but we know what they are. They are the vectors corresponding to the symmetries of these two morphisms, right? It's unique, isn't it? I mean, the axis is unique of that symmetry and determines alpha 1.
Yeah, of course, alpha 1 is uniquely determined by S1, but
right.
This is the definition.
No, it's not uniquely determined. It's determined up to a constant, right?
Of course, the line of...
of course, but it's important to say. Because in the theory of Lie algebras, the normalization is very important. The whole integral condition depends on a certain normalization, right?
Yes.
So here, what is the normalization? You see my question? Either you tell me what the roots are, you cannot tell me the symmetries and not tell the roots, because the roots are not unique.
The roots are the elements which are W conjugate to alpha 1 and alpha 2. This is the definition.
I'm sorry.
So,
I didn't want to say that. What are the simple roots? That is my question.
Alpha 1 and alpha 2.
Can
These
you
are
give
two
me...
symbols.
No, I understand, except that in this case I believe they're not just symbols. You see what I mean?
No.
Okay, I
guess this is all self-contained. This is the definition which is self-contained. So I really don't understand what you mean.
No, if you give a name to a thing, okay, it means this thing is defined. Now you tell me that there is more than one alpha 1 and one alpha 2. This is what you're telling me. Because when you say it's formal, it means this. It's like we say, let's take a group G, and then our group is Z2. This is the same situation, right? I mean, it's, alpha 1 and alpha 2 are not just names. Alpha 1 and alpha 2, we know the lines, because they are determined by S1 and S2. Okay? No, it's not true.
Because we started with the lattice. We started with the lattice, which is generated by alpha 1 and alpha 2.
Okay.
These are two symbols. On this lattice, I can consider these automorphisms. And that's it.
Okay. So for the moment, alpha 1 and alpha 2 can be anything. That is the thing. Okay. No, I'm sorry, I was missing.
And they're the basis of Q.
No, I understand, but I'm saying that they don't have a specific...
They are not element of the duals or...
No, they're nothing. They're just... okay.
We don't have a Lie algebra.
No, I'm aware we don't have a Lie algebra.
So we are just considering this...
I forgot to check Kat's book. Okay. No, sorry, I understand.
Yeah, so maybe your question was about this normalization with respect to the Cartan-Savart. So that
No,
makes sense, but we don't have a Cartan-Savart.
No, because for now, really, for example, all the rank 2 Lie algebras will fit this situation, for example, right? This is very general.
Yes.
And more will fit also. So for now we're very general, that's the thing. Okay.
Yes. Just looking at the root system, the root lattice, forgetting the origin in the Lie theory. Okay, so that was generated by these two elements. And we have this fact that the group is finite if and only if BC is at most 3. So this happens in exactly 3 cases: B equals C equals 0. Remember that the matrix was sign-skew symmetric.
No.
So either they're both 0 or they're both or they have opposite sign. So B, C equals 0, B equal no, they are both positive, because then we change the sign in the matrix. So this is a possibility. B equal 1, C equal 2, or B equal 1, C equal 3, or vice versa. Clearly, the situations are symmetric. In these 4 cases,
what does it mean? They can be both positive or both negative, but, right? No.
So in our situation, they are either both positive or both 0.
Ah, okay.
But then the matrix corresponding to B, C will be 0, B minus C 0.
Okay. This is our convention, okay.
Which must be sign-skew symmetric. So
this is the matrix B, right?
But B and C are always the exponents.
This is the B matrix.
Yes, this is B. This is B of T 1 or B of T3. This is B of T odd index. Okay. So these 4 cases will correspond to the 4 root systems of rank 2 associated to the algebras of finite dimension. So this is the case. If you know what this means, A1 times A1, this is A2, this is B2, and this is G2. Okay. So the roots, as I was saying, are all elements in Q, the root lattice, such that beta equals W alpha I for some W and I equal 1, 2. And it's also part of the theory that phi can be split into 2 parts of positive and negative root. Phi plus is the element, given by the elements of phi, so these are the roots, which can be written as C1 alpha 1 plus C2 alpha 2, where both coefficients are non-negative. C1, C2.
Okay, yeah, then we know for the W finite, for generic, I mean, do we know this? I mean we have to prove
Yes, this is always true, and the proof is exactly the same.
yeah, I mean, you have to prove it though, it's not...
You have to prove it, but I don't want to prove facts about the root systems which are fairly known.
No. C1 and C2. So first of all, the roots now are infinitely many, right?
Yes.
Possibilities.
Yes.
Secondly, C1 and C2 will still be integrals, integers, right? C1 and C2.
Yeah, this comes from the definition.
Comes
if you
from-
apply S1, S2,
Right.
S1, S2, you
So-
always get...
Okay. And the proof will be the same. You use an hyperplane that... now,
You take a regular vector and...
yes, the thing is that now the fact that it's not finite, the set of roots, will introduce an extra complication because how you choose this hyperplane, right? You remember the proof?
Yes.
I mean, in choosing the hyperplane, you're using, it is easy because you know that the roots are finite, so you can miss easily them, right?
Yes.
Here you don't have this, I mean, you have a little extra complication, no?
Yes, but you just have to choose a vector which is not orthogonal to alpha 1 and alpha 2. So which is not fixed by S1 and S2, and then the proof goes on, I guess.
No. The proof that root system admit base starts with choosing an hyperplane that misses all hyperplanes.
Not an
Isn't-
hyperplane, a regular vector.
Whatever, is the same. Regular vector is orthogonal to unique hyperplane?
Yes.
No, perché adesso...
Yes. And what is this? It is an element which is not orthogonal to these two.
No, don't you want it that is... no, I'm asking because I don't remember. Don't you want it that is different from all the roots in the root system, not just the two base ones? Don't you want that? Because all the roots will lie on... positive will lie on one side, negative. Isn't this that you want when you define it?
I want it. Yes, you're right. You're right.
No, but I'm telling you because it is clear that these are numerable, right? I mean,
Yes.
so you can pick, but it's an extra complication. I mean, these are these little arguments that one has to be careful, they're delicate. So here is extra complication, I think. I'm not saying it's not possible, I'm saying beware, there is a problem. It's just to make fun because you said the proof is the same. It's not the same. Cosa pensi, Fabrizio?
Okay, I don't think it's a...
No, I don't think it's a problem, but I'm saying that it will introduce extra complication because of the infinite possibilities for this.
Okay, yes.
I think Biaggi knows there is some clever argument, right? Saying that this will form a closed into so there will be, I mean, since they are countable, they will. There is some clever argument that a student wrote in an exercise because clever arguments I never get. The students will get.
You need to show that
It is possible to choose.
That Rn cannot be a countable union of R.
Right. There is some analysis, clever argument that says like the Rn cannot be a union of a countable hyperplanes. Biaggi, you know better than us.
Beh sì, i iperpiani non sono nowhere dense.
Esatto, perché it's a bare category.
category.
I know, it's bare category. So Biaggi knows the argument.
Ok.
C'è da usare, capito, qualcosa
Sì, basta prendere i vettori ortogonali, così scrivono una sfera.
Sì, sì.
Se sono numerabili non possono scrivere tutta la sfera.
Esatto, sì, c'è un argomento così.
Che non è numerabile.
Sì, anche così, sì, sì. Anche Fabrizio produced a better argument.
Ok.
Ma quanto rompe poche parole, vabbè.
So these are the positive roots. And the set of roots phi is the union phi plus and phi minus. Well, of course, phi minus is minus phi plus.
You know, I'm very careful in this because in the super world it's not true that phi minus is minus phi plus. So it's very irritating. Very irritating.
Phi plus is minus.
Yes. These are the opposites of the positive roots. If beta is a positive root, then minus beta is a negative root. And the set of positive roots can be described in this way. Maybe I introduce the letter H. If W is finite, and the cardinality is 2H, which is necessarily an even number. Because in this case, the elements of W are the identity S1, S2, S1, S2, and S2, S1, up to S1, S2. H elements equal to S2, S1. In this case we have, and this is always a dihedral group.
Dihedral.
Yes, it is a dihedral group with 4, 6, 8, and 12 elements.
What is direct inspection, this fact?
Yes.
Okay.
Yes, and positive roots phi plus can be expressed in this way. One notation.
Non ho capito quello che hai scritto.
W1.
I mean, H, A must be, there are not a lot of possibility for H because...
Yes, H can be 2, 3, 4, and 6.
Okay.
Corresponding to the...
Io non ho capito quel H equal A. Ah no, H, I see, H a number, okay, I see. I thought H was an element, no, H is a number, okay.
H is a number.
Okay.
The Wien group has 2 H elements, which are these elements. So in all cases we write W1 of M as the product which starts with S1, S2, and S and letters, and similarly W2N if the words starting with S2 with N letters. Okay. And phi plus can be described in this way. This is W1 M of alpha n plus 1, where with these brackets I mean the unique element between 1 and 2, which is congruent to m plus 1 modulo 2. So if m is odd, this is 2, and if m is even, this is 1. This is just a notation. And here m goes from 0 to h minus 1. This is if W is finite. And the other case, if W is infinite, then we have W1M alpha n plus 1 and greater or equal than 0 union W2 and alpha n and greater or equal than 0.
So this is a statement.
If W is infinite.
This is a statement.
Oh, yeah, this is a statement which is also known in the theory of root systems. So, how can one prove this?
What is alpha n plus 1?
So n is an element between 1 and 2, given by n is congruent to
Ah,
n mod.
don't write too far. È meglio che forse non scrivila in fondo perché
Yes,
si
yes,
fa
that's
fatica. No, lì vabbè, però insomma sì,
So just for the definition of this
Sì, sì.
symbol.
se no non si capisce.
In general, if you apply an element of W to a simple root, say to alpha 1, then you obtain a positive root if the element W does not have a reduced word which ends with the reflection corresponding to the root. So if you apply an element to alpha 1 and you want a positive root, this element cannot end with S1. So these are exactly all elements which are described in this way, and they are all distinct. While in the finite case, there can be repetition, and this is a set of distinguished elements in the set phi plus. So these roots are all distinct. And this can be easily checked case by case.
So you're relying on case by case analysis. There is no theoretical. I mean, can you briefly tell me why theoretically this is true? Because I know something about root systems, so maybe I understand.
So that.
No. If it is, don't prove anything. Just the idea, if there is an idea, because I don't believe it's root by is case by case analysis. I don't believe it. No, don't you think? There is more to it.
In this case, you mean?
Yes. So they
So,
say.
so you can easily prove that these are positive roots. That can be done as I was saying before. If you apply an element which does not have a reduced word which ends with a reflection corresponding to the simple root, then you always obtain a positive root.
Let me see, because...
So in this case, W1M...
Because the parity is different.
Yes, if this ends with
So
S2, then you apply it to alpha 1.
But then, there don't you want W2M plus 1, alpha M, downstairs, in the other one?
No?
No, you want the same parity? You see what I mean?
So let me see. If this, say for n equal to 2, this ends with 1, and you apply it to alpha 2. That's correct.
Because you're changing, you're changing from W1 to W2. Okay.
Yes.
No, okay.
The last letter should not be the same as the index of the...
So you stay in the positive roots. Then they will be all distinct. I don't see. Why should they be all distinct? You reach
So
because
this is a
No.
proof that they are all positive.
yeah, but then you
Then they are also of the right number, but I cannot
yes,
see
No,
why
because-
they are all distinct.
no, because you no, okay. You apply the when you reach the maximum length, right, of W1, cannot be of length whatever, right? It can only
Yes, when you obtain a
right.
length h. If the W1M is this longest element, and
Yes.
this has two expressions, two reduced expressions which can end either with S1 or
Mhm.
S2, so you are not allowed to apply this to a positive root and obtain a negative root.
Right. So it's
Maybe you can make an example. Maybe,
no. It's
No, I
no.
want to show the example.
No, but I'm happy. I sort of see how. So the only thing is don't you use the uniqueness of expression of your group, right? Because until you reach, I'm wrong. Until you reach the maximum length, it doesn't make, no. Okay, there is some work to do, but okay. No, don't do it. We don't need to see.
No, because we apply them to different elements. So in the case of A2, what happens to A2? Who is P plus in this case?
No, it's so H is equal to 3, right?
Yes, H is 3. So
Then
we
you have a three
have for M
positive
equals
roots.
0, we have alpha 1.
So,
For M equal 1, we have S1 of alpha 2. And for M equal 2, we have S1, S2 of alpha 1. Who are these elements? S1 of alpha 2, of course I have erased this, but
You can make the
this is
little
alpha 1 plus alpha 2.
you can make a little picture, right?
Yes. S1 was 1, 0, 1, 1 in this case. S2 is 1, 1, 0, minus 1. So S1 of alpha 2 is alpha 1 plus alpha 2.
That is not the picture.
That is not
The picture.
the picture.
The picture.
Oh, the picture. No, I don't want to do the picture.
You know. Yes, because in that way you normalize it, right? Always. Because you're choosing a basis for which alpha 1 and alpha 2 lie on the axis, isn't that right?
Yeah, that's the definition, yes.
So it is kind of not.
I mean, the root lattice is always
Right.
generated by the roots, by definition.
No, but I'm saying that we are choosing for Z2 a basis, a Z module that makes the roots on the axis, right? If we write that way. I mean, there is a picture of A2 we have in mind. This is not the picture that comes out from here. That's all I'm saying. No, Fabrizio, do you see what I'm saying?
No.
No, okay. What is the picture of A2? A2 can be drawn, right?
Yes.
Wonderful. This is A2. What I'm claiming is that S1 and S2 are not the reflection with respect to these hyperplanes. Am I wrong?
So alpha 1 and alpha 2 are these two vectors. This is,
Yes, in the picture these are the two vectors.
yes.
But
So
if
we consider the lattice generated by these two elements.
yes, but S1 and S2 will
Yes.
not act on this lattice.
Yes, they will.
They will? Okay.
By definition.
Can we see? I'm sorry, I
Yeah,
don't
of course.
see.
If I apply S1 to alpha 2, I obtain alpha 1 plus alpha 2, which is this.
No, but this is not
This is
right.
an element
I
of this
mean,
lattice. Yes.
Okay.
The lattice generated by alpha 1 and alpha 2.
When I write a matrix,
Yes.
you are fixing the basis alpha 1 and alpha 2, okay?
Yes.
No, va bene, okay.
Yes.
No, I understand. Because writing like this one
But
thing
I can
about...
also draw it in this way.
Right, that is the misunderstanding that happened to me and could happen to someone else.
But this is also correct.
No, I know
For
it's
our
not
point of
correct.
view.
I know.
Yes.
It's not wrong. except that all the Lie theory is based on the other pictures, so it's, at some point you need a form of normalization, don't you? No, never in this theory.
The normalization comes out if you consider the Cartan-Savage.
Ah, only, okay.
Yes, because then the roots are elements of a dual of a vector space which is defined, so here you need a normalization. Right? In this abstract context there is no
Non rompo più,
normalization.
sto zitta. Va bene.
So we have alpha 1 plus alpha 2, and then S2 of alpha 1 is alpha 1 plus alpha 2, and then we apply S1. S1 of alpha 1 is minus alpha 1, and S1 of alpha 2 is alpha 1 plus alpha 2, so this is actually alpha. And this way we obtain the three positive roots. Of course, if we consider S1, S2, S1, is this element S1, S2, S1, which is equal to I want to say
Devo attaccare la elettricità.
I claim that this element S1 is given by this matrix. This will be needed later. This can be easily checked. If you apply this to alpha 1, you obtain here minus alpha 1, and then minus alpha 1 minus alpha 2. And then by S1, then alpha 1 minus alpha 1 minus alpha 2. So we have minus alpha 2. Let's see right from there. Cos'è questo concetto?
Non ce la posso fare.
Which proves in particular that the group is finite in this case.
Allora io te lo metto qua, non ti ammazzare. Provo, metterlo qua. Ma non ci arriva.
Okay. So now we consider this map.